Hey everyone, welcome back. Today we're going to be talking about the Pythagorean Theorem, which is an equation that we use to help look at the relationship between the side lengths of a right triangle. And by a right triangle, I mean one that has a 90-degree angle in it. We usually look at a triangle and see a box in it like this. That means it's a right triangle. Can I use a sword in this video? No? I mean, it could be like part of a triangle. I can put a marker on the end of it. Come on. Hey, are those my fruit snacks? Looking at the parts of a right triangle, we know that this box means this is the 90-degree angle, which is what makes it a right triangle. And then we have three sides, just like every triangle. But with a right triangle, we actually call this a leg, we call this a leg, and then we call the long side, which is opposite the 90-degree angle, we're going to call this side the hippopotamus. We're going to call this side the hypothalamus, the hypertension. Alright, cut. One more time. We're going to call the long side that's opposite the 90-degree angle
the hypotenuse.
Now that we know the parts of a right triangle, let's talk about what the Pythagorean Theorem states. The Pythagorean Theorem is a fundamental relation between the three sides of a right triangle. It states that the area of the square whose side is the hypotenuse is equal to the sum of the squares of the other two sides. Okay, whatever that means, I'm going to give you one simple equation. So here's our right triangle with our 90-degree angle. I'm going to label each leg. I'm going to call this one A, and I'm going to call this one B, and then I'm going to call the hypotenuse C. The Pythagorean Theorem gives us an equation that tells us
A squared plus B squared equals C squared.
we have three variables, which means that if we know two of the side lengths, we can find the third side length. Or if we know these two side lengths, we can find that side length. Let's go ahead and jump right in with some examples. Okay, so here we go. We have a right triangle with side lengths of 3 and 4 for the legs and C for the hypotenuse. We know that A squared plus B squared equals C squared. So we can go ahead and plug right in, because here we know that our legs are A and B. So let's call this 3A. So we know A equals 3 and B equals 4. And C is what we're looking for. Let's go ahead and plug in what we know and see what happens. I'm going to take my A, 3 squared. Now I'm going to plug in my B, 4 squared, and it still equals C squared. Now, to square this term, I just need to multiply 3 times 3. 3 times 3 is 9, plus 4 times 4 is 16, equals C squared. Now if I add these two together, I'm going to get 25. 25 equals C squared. C squared means that C times itself, so it must be a number times itself, equals 25. So if I take the square root of each of these, I'm left with C equals, and 5 times 5 equals 25, so the square root of 25 is 5. Based on the Pythagorean theorem, I can find that the hypotenuse of this triangle is 5, which seems correct.
Because the hypotenuse is always the longest side.
And it is always opposite the 90-degree angle. Sometimes I draw an arrow out of the box so I know which side is the hypotenuse. Okay, here we go. This example is a little different. First of all, the triangle's upside down, but that doesn't change anything. The other part that's different is we actually know the length of the hypotenuse. Remember, it's opposite our 90-degree angle. And this time we're looking for the length of B, or one of the legs. So let's go ahead and write down what we know. We know that A is equal to 6. We know that we are looking for B. And we also know that the hypotenuse is 10. Let's go ahead and plug into our equation of A squared plus B squared equals C squared. A is 6. B is still the unknown. And C is 10. Let's go ahead and square what we can. 6 times 6 is 36 plus B squared. 10 times 10 is 100. Now we want to solve this just like a normal equation. We're going to go ahead and subtract 36 from both sides. And I'm left with B squared equals 64. Now all I have to do is take the square root of each of these. And B equals 8. Because 8 times 8 makes 64. And if we want to think about this, this checks out. B equals 8, which is correct. The legs are both shorter than the hypotenuse. Remember, the hypotenuse is always the longest side of a right triangle. Hey, thank you. Thank you. Happy to be here tonight. What does a triangle with a 90-degree angle and my wife have in common? They're always right. Okay, let's try another example. It's going to be a little bit different, and you'll see when we get to the answer why it's different. Here we go. It looks like I have both of my legs, and I'm missing the hypotenuse. So I'm going to plug into my formula of A squared plus B squared equals C squared. And I'm going to say 2 squared plus 3 squared equals C squared. Let's go ahead and square these terms. 2 squared is 4. 3 squared is 9. And that equals C squared. 4 plus 9 is going to be 13. All right, perfect. So C squared equals 13. What happens when we take the square root of 13? Nothing. We're left with the square root of 13. And that's okay. Our last two examples, what we saw were numbers that were perfect squares. This time, we end up with 13. It's not a perfect square. We can just write it as C equals the square root of 13. And that's perfectly fine. And if I still want to think about this, this checks out. So C equals the square root of 13. Let's talk about this answer for a second. C equals the square root of 13. How do we know that that's correct, right? C should be the longest side because it's the hypotenuse. Well, let's think about this. If we were to put this on a number line, let's say this is 1, 2, 3, 4, and 5. So this is our number line. We know that the square root of 16 is 4. We also know that the square root of 9 is 3. That means the square root of 13 is somewhere in between the values 3 and 4. Pretty close to being 3.5, not quite, which makes it the longest side. That makes sense. Do you kind of see how that works? Okay, let's go ahead and do one more. Here we are. We have our two legs and we have the hypotenuse. And I know that's the hypotenuse because it's opposite my 90-degree angle. So let's go ahead and write down what we know. It looks like we're looking for A. B is 6 and C is 12. Let's plug it in, okay? So we have A squared plus B is 6, 6 squared equals 12 squared. So I'm going to go ahead and calculate this out. I'm going to bring down my A squared. 6 squared, 6 times 6 is 36, and 12 times 12 is 144. Alrighty, so now I need to minus 36 from both sides. And A squared equals 108. Now, I'm going to take the square root and find that A equals the square root of 108. Once again, this one's a little different. I actually don't want to leave it like this. I can break this down a little bit further. Let's go ahead and take a look at that. I'm left with the square root of 108. And I want to go ahead and break that down. I know I can do more with this because it's an even number, so I'm going to factor it out and see what happens. If I take out a 2 and 54, right? It's a factor tree. You remember how to do this. 2 times 54 makes 108. I'll do it again. 2 and 27. 27 is 3 and 9. 9 is 3 and 3. Good. Now this is a prime factorization of the number 108. Let's see what I can pull out. It looks like any sets I have where there's 2 of them, I can pull them out from being inside the radical. This is the same as saying 2 times 2 times 3 times 3 times 3, right? So this is the same. I want to go ahead and see what pairs I have. I have a 2. I can bring that on the outside of the radical. I also have a pair of 3's. I can bring that on the outside of my radical. And I'm left with the square root of 3. Now I have 2 times 3 is 6 square roots of 3. Easy. Okay, seriously though, I can't even get this thing off. Oh my God.